So, today we will continue with our discussion on the introduction for tissue engineering. So, yesterday I had posed a few questions. I hope you had gone back and read a little bit about it. So, we will start with the first question. Which tissues do you think would be the easiest to engineer? So, yesterday you answered with a few. Did you find out why you thought those were the easiest, or did you have a reason for that?
The growing rate, how much time it takes.
That is one good reason. So, you actually, generally they regenerate well, so it might be easier to do. And you had mentioned skin, right? Okay. So, what else?
Easy to implant.
Okay. So, somebody had also mentioned cartilage. Do you think cartilage regenerates rapidly? No. Then why cartilage? So, what did you identify from literature?
I thought the function performed would be much simpler than something like maybe heart valves.
Okay. So, functionally cartilage is a simpler tissue. Yes, that's one reason why you would think it's easier to emulate that. Okay. Any other tissues which you thought of? Okay. So, what about bones? Yeah, bones are also reasonably easier to regenerate compared to most other tissues. So, what do you think is the common factor which you saw between all these tissues? They are basically just barriers or supports. They are not functional tissues, right? So skin is just a barrier, bone is just a supportive tissue, cartilage is also a supportive tissue. All those things are, as you said, the function itself is simpler compared to other more complicated tissues. So, which tissues do you think would be harder to engineer? Hard, why?
Because the growth rate is.
Okay, regeneration is very slow, that's one limitation. The functional.
The cells are very highly differentiated.
Okay. So, functionality of a hard tissue is very high. Along that lines, can you identify other tissues which would be even harder than a hard tissue?
No.
Nerves and brains, okay. So, brain, as of now, I don't think anybody is trying to engineer a brain. So, people try to look at nerves and like peripheral nervous systems and things like that. Lungs, okay. So, why? Why do you think it will be harder?
I'm just asking whether is it harder.
Okay, so
Specialized, right?
yeah, so if you're talking about lung as an organ, it's very difficult, obviously because of the architecture, and there are just too many things which are changing there. But smaller tissues, yes, it would be about the same level as a hard tissue. It would be the same level of complexity as a hard tissue. What about think of something which has a little more biological functionality.
Pancreas.
Okay, why pancreas?
It is actively performing.
Yeah, so pancreas needs to secrete insulin and glucagon, and it while it senses the glucose levels, right? So, it has very specific functionality. So, that is going to make it a harder tissue to engineer. So, similarly liver tissues. So, liver would be another tissue where you could still have similar challenges. So, these kinds of tissues which actually have to respond to stimuli are harder to engineer because there are some functionalities which you don't really, which you cannot easily recreate in an in vitro setup. Okay. So, what has been the most successful clinical application that has been commercialized? First, I want you to identify which are all the commercial products that you were able to find. Okay, I want to know the name of the product.
Dental implant.
Okay, I want to know the name of the product. I want to know what dermagraft. Okay, carticel. Carticel is for what tissue?
Cartilage.
Cartilage. Dermagraft is for skin.
Something called OP1 putty, but I didn't know what that was.
What?
Yeah,
what is it?
It's something related to the bone.
OP1 putty.
Yeah.
Okay, I have not heard of it. So, OP. So just OP number 1.
Yeah, OP number 1.
Putty. Okay. Oh, okay. So it is spinal fusion from Stryker. Okay. Okay, so it basically has recombinant human bone morphogenetic proteins. Okay, so what else? Have you seen any other commercial things? So the commercial ones kind of align with what you thought would be the easiest tissues to engineer, right? So another major reason cartilage is actually easier to engineer is it's an avascular tissue. So you don't need to worry about vasculature. Creating vasculature is one of the limitations in tissue engineering. So that can actually be overcome when you are working on avascular tissues. Okay, so we have looked at some of the commercialized ones. Actually, the most established commercial product is the skin. Because the first the tissue engineered product which was approved was a skin graft. So I think it was called AppliGraph, if I'm right. So, or no, Integra. I don't know, there are like multiple things. So the Integra was probably the one which was commercialized first and approved by FDA. So even with that, it's still not a full success. Can you think of why it is not a full success?
Sense of touch in that area where you're different.
Okay, so that would be one problem because innervation has to happen for the sense of touch, the sensory things to have, be there. That is one thing. So what else?
It's not yet fully biocompatible.
Okay, why do you think that is the case?
Maybe due to immune reactions caused.
Okay, so dermagraft, Ramya, you identified dermagraft, right? Do you know what it is made of?
No, I didn't write it down.
Okay, so it basically has a matrix on which cells are seeded. So it is it's not an acellular thing. So there is already, you are going to have some cells from other sources which can cause immunological reactions. So there are acellular tissues as well which are used. So I think Matriderm is probably one product where you use an acellular matrix which doesn't have cells with it. So but even with all that, your reinnervation is one thing, your sweat glands and this perspiration is one thing, where and aesthetic aspects where you have to have the hair growth or the matching the skin tone of the person, all these things can be a challenge. So because of these things, it's not a complete success. However, it has been reasonably successful to provide enough of a healing effect. And another major limitation you would see with most of these things are they are ridiculously expensive. So it's not like it can easily and readily be used by everybody for general use. Okay, so we already labeled and identified a few other commercial tissue engineered products, and all of them have their own limitations. One major limitation is the size of the tissue engineered construct itself, which is because of the vascularization or the lack thereof, which leads to very little nutrient supply, or supply has to come only through diffusion, and that is not the most efficient way for nutrient supply or toxin removal. Okay. So let us move on. So currently there are different ways to engineer tissues. So these are the, I have just segregated them, but as of now people do not try to do them independently, people try to prepare combinations. So as I had already discussed the tissue engineering triad, it follows the same pattern. You could either use a material or cells or molecules which can trigger the regeneration of tissues. So biomaterial delivery is where you use scaffolds or implants, and the host cells will have to migrate here, adhere to the material and help in the healing process. People use cell delivery as well, where you either use a transplantation of a cell population. So the cells will basically produce their own support matrix and integrate into a host tissue. So this is where you have the stem cell therapy and all those things, where you just harvest stem cells and supply it to the site of injury, hoping it will help in the regeneration, right. So those kinds of things are done for cell therapy. And you also can have molecular delivery, where you either use gene delivery or single molecule or multiple molecule delivery. So the product which Ramya identified, what is it, OP1 putty, right. So that is a recombinant bone morphogenetic protein. So bone morphogenetic protein is a growth factor which helps in the formation of bones. So delivering such a molecule would help in regeneration of the tissue. So currently people focus on combining these things. So people have seen that using them independently has its own advantages, but it can only help in regeneration to a certain extent. Beyond that point, you need to have a multifunctional material which can provide different avenues for regeneration itself. So, the materials which are used can be classified primarily as 4 things. So, they are the metals, ceramics, carbons and polymers. So, metals are basically titanium, gold, silver and alloys. Ceramics, it can be alumina, can be zirconia, hydroxyapatite, so many different ceramics are available. You have the carbons, which would be carbon nanotubes, pyrolytic carbons, graphenes, fullerenes. There are just too many options where you can try to use them. So, people have been trying to use these for different biomedical applications. Polymers, obviously there is a wide array. Whatever I have listed here is only synthetic polymers. You can also use natural polymers like chitosan, collagen. There are just a wide array of options which can be used. So, these are the 4 major classes of biomaterials, and composite is just another class which is basically a combination of these materials which we have said. So, people use polymers along with ceramics or carbons and to provide different functionality. We will go into a little bit of detail of all these things, and hopefully we will have more discussion in the subsequent lectures. So, metals can either be a single metal or alloy. So, some examples for alloys which are used in biomedical application would be stainless steel or nitinol. The advantage is they are strong, tough and ductile. However, the disadvantage is they may corrode and they usually have very high density. So, this would mean there could be discomfort for a patient when it is being implanted in the body. So, that could be a limitation. So, metals are used as biomaterials in many cases. Some of the options are where you use it for structural components like hip and joint replacements, bone fracture pins and plates which is used during surgery. You also have dental implants where metals are used. So, other applications would be for cardiac devices, stents, wires and tubing. So, what you see here, this is actually a stent. So, this is how a stent looks, and this is used to make sure the blood vessels do not collapse. So, in case of angioplasty, that is where it is done. So, you actually put the stent there and it helps to keep the blood vessel open. And nitinol is one alloy which is quite popular. How many of you know what nitinol is? Does anybody know what nitinol is? Okay. So, this is a super elastic material which is used in vascular stents. I hope this video plays. Okay. Let us see if it plays. Okay. I really did not want the audio. So, that is just a water bath you are looking at. So, what you have here is just a water bath, and the wire which they are playing with is the nitinol wire. So, any kind of deformation, it will again go back to its shape provided the environment is right, like temperature and conditions, the physiological conditions, it will actually go back to its original shape. That is why it is called as a shape memory alloy. It can retain shape and elasticity. So, this can be deformed for easy implantation. So, you do not have to open up the patient all the way to put this in. So, and it restores its original shape inside the body. So, that is why in angioplasty all they do is just have basically a catheter which is put inside the person's body, either through the wrist or through some blood vessels between the thighs. So, that is what is usually done. So, it is a simple enough procedure because the material can actually be deformed and it will regain its original shape once it is implanted. So, people are now looking at developing these stents for different applications. So, recently there was an FDA approval for even bifurcation stents. So, when there is a clog in the blood vessel, a stent is placed so that the vessel can be kept open, right. But what can happen is these kinds of clogs can happen at the point of bifurcation of blood vessels. If that happens, keeping one stent is not sufficient. So, what people tend to do is they put one, cut it open and place another. It is actually a very cumbersome procedure to do that. So, now recently there has been some approvals which have come out for bifurcation stents. So, some approvals had already been obtained in European Union, but recently it was approved in FDA as well. So, major problem with metallic implants is effect of corrosion. So, this would affect the surface and the bulk properties. It also alters the way the material interacts with the host, right, because you are now having a different surface morphology, even the chemistry is different. So, you do not know how the cells are going to react to it. So, it can cause problems. So, it can also cause serious volume change. So, if you are going to use something like iron, and it again obviously you would not use iron, you would use stainless steel or something, but there is going to be a significant change in density when you have some corrosion. And if the density for iron is 7.8 roughly, and the iron oxide is close to 6, you have a significant difference in volume which you are going to have, and this will cause major discomfort for a patient. So, the image you see here is actually a new implant, so it is for a hip and joint replacement. So, you see the one on the left side is the actual new implant, and the one is basically taken out from a patient after a few years. So, you can see there is some amount of corrosion, and this can actually be a problem, right. So, that is one of the reasons metals are usually an issue, and that is why people use very specific metals which can prevent this kind of corrosion. The image shown here is actually for titanium. So, titanium is one of the more stable materials, and even with that you have this kind of a problem. So, ceramics are basically inorganic compounds that contain metallic and non-metallic elements for which you have interatomic bonding, which can either be ionic or covalent, and these are generally formed at very high temperatures. So, a glass mug, a mug you use would be a ceramic, right. So, these are hard and brittle. So, they are very hard, but they break very easily. They have good thermal and electrical resistance, they are good insulators. They are also resistant to high temperature and severe environments. So, ceramics are used as in biomedical applications. Where do you think ceramics can be used widely? Which tissue would you want to use? Bones and dental tissues is where you use ceramics, because that is where you have ceramics in your body. So, it is used again in structural components like hip and joint replacements. So, you do not use the ceramic completely for joint replacements, because as I said, they are brittle. So, you would not want to place only a ceramic there. So, but it is used as a coating, or it is used in ways that it can help in cell infiltration and so on. So, spinal fusion devices can also be ceramic materials, and dental crowns which are commonly used. So, if you undergo something like a root canal, you would have to get a dental crown, and that would you can use ceramics. You can also use metals, that is what people used to use. Now, to make sure it fits with what you already have, people use ceramics. So, other applications would be cochlear implants, coatings on heart valves. So, in tissue engineering, can you name any ceramic which is used?
Hydroxyapatite.
Okay, so why hydroxyapatite?
Because it's part of the bone already.
Okay. So, your bone tissue contains hydroxyapatite. So, your bone actually has two components. So, one is hydroxyapatite, which is in the nanoparticle size, and this hydroxyapatite is actually the discontinuous phase. The continuous phase is collagen. So, collagen with hydroxyapatite composite is what your bone is. Okay. So, that is why it is a nano composite. A bone is actually a nano composite material. So, some of the ceramics which are used are alumina, zirconia alumina complexes. So, these are bio-inert ceramics. So, bio-inert ceramics would not promote bone ingrowth. So, you can have bioactive ceramics which are the hydroxyapatite and tricalcium phosphate and so on, which will promote bone ingrowth. So, there are different types of calcium phosphate bioceramics. Hydroxyapatite is the one which has the calcium to phosphate ratio closest to the one in your bones. So, that is why hydroxyapatite is extensively studied for bone tissue engineering. So, tricalcium phosphate can also be used. So, you can actually tailor the degradation rates by using different types of tricalcium phosphates. So, that is why people try to use that as well. So, people are using bioactive cements and porous scaffolds and composite scaffolds for tissue engineering. So, people also try to emulate what you see in the body, right. So, people try to use polymers along with ceramics, so that you can actually create bone like tissues. So, carbons are basically just different types of different allotropes of carbon can be used. Pyrolytic carbon is used as a coating for mechanical heart valves. Diamond like carbon is also used for coating on heart valves and blood contact devices, because diamond like carbon has very good hemocompatibility. So, you use it for coating on blood contact surfaces. So, carbon nanotubes also had a lot of interest in the last couple of decades probably. So, it is being used for biosensors, bone regeneration and other gene and drug delivery and so on. In the recent past, graphene and graphene type compounds, type components are also used. So, graphene oxide, reduced graphene oxide, all these things are being explored. So, the image you see here is actually a TEM image of reduced graphene oxide. So, this has been used in biosensors and also for drug delivery, and it has very good antibacterial properties. So, it is being explored for coating on implants and so on. So, recent studies have also shown that at certain concentrations these graphene oxides and reduced graphene oxides can help in vascularization, whereas at higher concentrations they will inhibit angiogenesis. So, you can use it at different concentration. If you use it at higher concentration, you can probably use it for treating cancers, while if you use it in lower concentrations, you might be able to use it for promoting angiogenesis in tissue engineering. So, obviously most of these carbons, there are a lot of detractors for it, because people are worried about the long term effects. So, there are very few studies on the long term toxicities of such carbons, because see these are nanoparticles, and toxicology of nanoparticles itself is a major question mark which is being explored. So, this being a carbon which has not been established for a long time raises serious red flags in many cases. However, the promise which these materials are showing has made it an interesting material to work on, and there is a lot of research which is happening in this domain. So, moving to the polymers. So, this is where I work. So, most of my lab students work on polymers. We try to develop different types of polymers and polymer composites for various applications, either it could be for an implant application or drug delivery application or tissue engineering application. So, here which type of material, which polymer you use would be driven by the tissue you are trying to regenerate. So, you try to design polymers in a way that it will be similar to the natural tissue itself. So, these things I am assuming you already know. Poly is many, mer is the unit, polymer is basically a repeating units. So, these are non-metallic components which form macromolecules. It could be chains, branch chains or cross-linked networks. They have poor thermal and electrical conductivity. However, there are some conducting polymers as well, which have been used for nerve tissue engineering and so on. So, polymers are one of the most widely used biomaterials, because there are just too many types of polymers. Each polymer has its own properties, physical, chemical and biological properties. They are so vast. So, it has been used in all possible applications. So, valves, ducts, catheters, joint replacements, it is used in coatings, encapsulants, tissue engineering scaffolds, lenses. From anything from blood bag to a tissue engineered scaffold, you are looking at using a polymer, right. So, there are just a wide array of applications that you can look at, and depending on the application you would be looking for very different properties. See, if you are going to use it as a lens, what would be the property, a lens for your eye, what would be the property you would focus on? Yeah, transparent. And so, what about if it is going to be used as a blood bag?
It shouldn't affect the blood inside.
Okay. So, it should not trigger coagulation cascades, right. So, which means it should be hemocompatible, it needs to be blood compatible. So, blood should not, the platelet pathways should not get activated. platelet should not start adhering and clotting. If that happens, the blood will be unusable. So, each material has to be uniquely different, and people try to engineer these materials. We try to modify surfaces to provide desirable properties. So, PMMA is used there, and mostly people do not use polymers by themselves. It will again be used with right now people use it with other combinations with ceramics and so on. So, polymers in tissue engineering, again collagen is the gold standard, because that is what is present in your body. So, you have collagen as the major component of your extracellular matrix. So, people try to use collagen. However, collagen can be expensive if you are going to get it as a highly purified form. You could try to extract collagen from other sources. So, you can get it from any source, right? Any tissue would contain collagen. So, if you were to take just chicken skin somewhere and you start treating it, perform the proper procedure, you can actually extract collagen. However, collagen is not the only material you want to use. So, people are trying to look at different things, because collagen, see, when you talk about natural materials, you can always have batch to batch variations, and there is also a risk of contamination. So, considering all those reasons, people try to use other sources. So, polysaccharides are again natural sources. You also have PLA, PLGA or PEG and so many other materials which you can use, which PVA, all these things are used which are synthetic materials, where you have very good control over the molecular weight, which means the physical properties can also be controlled very well, right. So, people try to use so many different materials, and these materials are also fabricated differently. So, what you see here are different fabrications. The first one you see is probably just a lyophilization and freeze drying, freeze thawing technique, which creates a lot of pores. And the next one you see is just a solvent casting technique, where you have something like a hydrogel, a smooth surface hydrogel. And the one you see after that is actually the electrospinning, where you get nice fibers which could be of nano diameters. And the next one is more like a printing, where you get or molding, where you get specific structures. So, there are just many fabrication techniques. We will go into the details of the fabrication techniques when we talk about the individual materials. So, composites can be anything. Composites are basically polymers and ceramics put together would be a composite. A collagen hydroxyapatite is a composite in the bones, and you can have polymers and carbons combining to form conducting composites. So, people have looked at putting a polymer like PCU along with graphene to show whether it can improve the electrical properties. So, polymers can also be blended with metals like metal nanoparticles to provide antibacterial property or to deliver drugs and so on. So, that covers the aspects related to materials. So, you also have cells which can be delivered, right. So, that is the next part of this work. So, how do you deliver cells? So, what cells do you choose to deliver? So, again it depends on the cell source and cell types. Cells can come from different sources, it can also be of different types. So, we need to identify what cell source we want to use for a specific application, and what would be the cell type you would want to use for the specific applications. So, the sources I have classified as autologous, allogenic and xenogenic, and types I have classified them as differentiated and stem cells, and just put other types of cells where you can use a cell type which is not directly related to the tissue you are looking at, okay, or you can look at co-culturing and so on. So, let us look at these cell sources first. What do you think would be the advantage of using an autologous cell? No immune response, it is from your own body. So, there is no chance of any immune response, okay. What would be the disadvantage of using an autologous cell?
Invasive procedure.
Okay, invasive, sorry?
Limited amount.
Limited amount, okay. Anything
cause
else?
problems in the tissues, like the location you're extracting.
Yeah. So that's called donor site morbidity. So basically you are damaging another tissue to harvest the cells, and if a patient is already suffering, creating another damage to the tissue can actually be a problem. So what about allogenic transplant, allogenic cells? What would be the advantage of allogenic cells? Allogenic is from same species, some other person. So what would be the advantage?
Abundance of
Higher availability.
Abundance, okay, sorry, higher?
Higher availability.
Yeah. So it's more easily available. Disadvantages would be
immune response.
potential immune responses and rejections would be a limitation. What about xenogenic from another species? So much easier availability, right? So if you're going to get tissues from an animal, you're probably going to get more of it, and it's much easier to get animal tissues compared to human tissues, right? So and ethically also it's a little easier to justify doing something like that. So what about the limitations itself?
The rejection.
Rejection would be the major problem, right? So that's what I have here. So basically you have limitations with all these techniques. So you need to look at how you would optimize it, right? So people try to work on this, people try to develop technologies so that they can expand cells. So you can only harvest a certain number of cells, right? So you cannot harvest all the cells you need for creating a tissue. So you harvest some number of cells and then you grow the cells. So you provide the right environment, right nutrients so that the cells grow, and then you can use this cell population for regeneration. So that is what people try to do, and because of this people have developed different technologies for different types of cells themselves, and people are working on improving this further. So what about cell types? So I said differentiated cells and stem cells. What do you think would be an advantage of using a differentiated cell?
If it's a functional tissue which you are making, then we will know that at the tissue, that is the tissue which we are going, that is the cell which will be there. And that
Okay. So you know that the functionality is already there. Okay. So that is one advantage. The tissue is already a functional tissue. What would be the disadvantage?
Differentiated cells don't divide. So
Okay.
difficult to actually.
So they will actually be very slow in growing, so you would not be able to get enough numbers. So that can actually be a major limitation. So what about stem cells? So stem cells actually can be from different sources. It can be from adults, from fetuses, or they can be embryonic, and you also have iPSCs now. Okay. So there are different types of stem cells which are available. So we'll go into details of each of them later, but right now what would be an advantage of using stem cells?
You can differentiate it into any type of cell.
Okay. So you can provide the functionality you want. Okay.
These are abundant.
Much more abundant and easy to harvest, and they will divide faster, they will grow at a much faster rate, making it easier to culture them. What would be the disadvantage of using a stem cell?
You have to provide the right factors for it to differentiate.
Okay. So controlling the differentiation of stem cells can be a challenge, especially in vivo. So in vitro differentiation is one thing, but if you're going to use a stem cell and you're going to use it in vivo, if you're going to implant it as a stem cell, how do you control the differentiation of the stem cells in vivo? So that becomes a different kind of a challenge. Okay. So what else?
Cancer.
Yeah, can you explain? What you're saying is correct, but
Like unregulated growth basically.
okay, uncontrolled growth can lead to teratoma formations, especially with respect to embryonic stem cells. That's a problem. So you can actually have that issue where it forms into a teratoma, and that can be a whole new complication you have developed now. Okay, so that's what I have here. You have required functionalities with differentiated cells, but stem cells can give you different functionality, can actually be differentiated to specific functionalities, but how you differentiate them in vivo is the challenge. Yeah, so, you would have to take into consideration all these things while you are developing your product or the problem statement. So, as far your project goes, do not just choose a stem cell because it just sounds cooler. Okay. So, you would have to justify why you would want to use a stem cell for this application. If you are going to work on something, make sure you have a strong reason to do this, right. So, cell therapy, there are different types of cell therapies which are done even today. So, people use it for local repair of tissues. So, injection of exogenous cells, especially chondrocytes for cartilage repair, disc cells for herniated discs, stem cells treatment for spinal cord lesions and brain lesions are all commonly done. People also look at injecting myoblasts and stem cells for treating myocardial infarction. So, cells for regenerating retina and joints are all stem cell therapies have all been done. People, some of them are experimental, some of them have been reasonably established, although there might not be enough of case studies or like a proper clinical study to prove its efficacy. Some of them have that, but many of them may not. So, you might just have doctors taking cells and injecting it, and considering that it is basically it has a lot of growth factors. When you draw some blood or anything, it will have other factors which will help in regeneration anyways, and people try to see that will be effective. So, one example would be platelet rich plasma therapy or platelet poor plasma therapy. So, all they do is take the blood out and spin it out to get the plasma, and this plasma either with platelets or without platelets or like with very little platelets can be injected to damaged tissues, and people have seen that this helps in faster regeneration. So, that is because plasma has growth factors, and you have all the signaling molecules which will probably trigger some kind of healing mechanism. So, people have shown such things. Okay. So, one of the major places where cell therapy has been quite successful and has been studied reasonably well for a long period of time is chondrocyte implants for cartilage repair. So, we will look at that as an example. So, what you see here is an articular cartilage defect. So, how many of you know what a cartilage is first of all? So, we all say cartilage tissue. Have you seen a cartilage? Like, you do not think of a human cartilage, you can think of an animal cartilage which you would have seen. Yeah. So, where have you seen an animal cartilage?
Chicken.
Chicken. Where do you see it?
The bone, it's just on the bone, sir. Not
Yeah,
sir.
on the surface of the bone. So, if you have eaten chicken, what you would have seen is the leg piece of the chicken would have a glassy material on top. So, that is the cartilage. Okay. So, the one which is shown here is a knee cartilage. So, this articular cartilage defect can actually be very painful. If you have a damaged cartilage, your walking would be a painful process. So, because of this, the quality of life, especially for elderly patients, is significantly affected. This damage can also happen for athletes during some injuries, or if you are in an accident and so on. So, age, trauma, all these things can cause these kinds of damages. This is quite common. So, a lot of people have this. So, do not confuse this with a ligament tear. Ligament tear is different from a cartilage defect. A ligament is basically just an elastic tissue which ties the bones together. So, the ligament tear is different from a cartilage defect. Cartilage defect is a lot more painful. So, cartilage is an avascular aneural tissue, and it does not heal on its own because it has very low cell density and they are very low mitotic activity. There is also very little cell migration to these tissues. Because of this, this tissue does not heal on its own. So, you need to provide some kind of a supportive environment for it to heal. So, people have tried to do different things. So, we will look at some of the therapies which are currently being employed and how they have been established. So, one term you would have seen is arthroscopic debridement. So, it is also called as scoping the knee or arthroscopy. So, people who follow sports would have seen this quite commonly. So, many athletes go through this. So, this is basically just a cleanup procedure. So, when your cartilage damages, what you are going to have is small bits and pieces which are going to be lying around. So, this is going to cause more pain for the person. So, this scoping the knee basically just removes the damaged cartilage and cleans up the place so that it can heal in a better fashion, so that there is no continued injury. So, effectiveness of this kind of a procedure has been questioned with respect to its healing effect itself. However, it will definitely help in reducing the pain and alleviating the suffering of the patient. So, Graham Smith is one cricketer who got it done, I think like 7 years back in 2011 or so. So, I am pretty sure a lot of soccer players would have gone through something like this, and basketball players, all these people go through scoping the knee quite regularly. Another procedure is mosaicplasty. So, here this is basically an osteochondral autograft. So, what is done here is, so this was developed by Dr. Hangadi, and when you have a cartilage damage, so you take out, you clean this out and you take pieces of cartilage from a non-load bearing area and you use that to fill it as pegs. So, if you can see this image, I do not know if it is very clear here. So, this is a damaged cartilage and they have actually taken small pegs from here. So, and from these small pegs they have filled the pore, which is filled the damage here, and you see that with the filled pegs, right. So, are you able to see it? Okay. So, that is how mosaicplasty works. You can Google for more images which actually show surgical images. So, this is a very simple procedure. However, the problem is you are now damaging another part of the cartilage. Knowing that cartilage does not regenerate very effectively, you have now anyways created another damage. The only thing is it is in a non-load bearing area compared to a load bearing area. So, hopefully the pain will be lesser for the patient. So, another type of surgery is a microfracture surgery. So, this is basically, this was developed by Dr. Stedman from Colorado, and here what is done is small holes are made in the base of the cartilage defect. So, again for any cartilage procedure, scoping would be the first thing they do, they will basically clean the cartilage. Okay. So, after cleaning it, they will create small holes and this punctures the surface layer of the underlying bone, and this will lead to bleeding of the bone, and the blood which comes out will clot, and this will contain stem cells and other growth factors, and this basically forms the tissue which will then help in regeneration. So, this is very commonly done for basketball players and like American football players. I do not know, soccer players are probably doing this too, not a big soccer fan, so do not know. So, this is a very common procedure which is done. This actually is a very serious surgery. The patient can take up to maybe a year for them to fully recover and get back to their full health. Okay. So, they might be able to do regular activities after a few months, but if you are an elite athlete and you want to get back to that level, it can probably take up to a year. So, the problem here is that the recuperation time is quite long, and also you are causing damage, and it can be a very painful procedure. You are actually drilling holes on a bone, and that is not really going to be an easy thing to survive. So, arthroplasty is basically replacing damaged tissue either using partial or total joint replacement, and depending on how bad the situation is. Okay, so, these are the current treatments which are done, and I want to look at the tissue engineering based treatments from here on out. So, that is a autologous chondrocyte implant. So, this procedure was first done in 1987. So, it has been a little more than 30 years, but it is still considered to be experimental by many people. So, even after 30 years, people still are exploring this further, trying to optimize it, make it better and so on. So, this was popularized by Dr. Lars Peterson. So, here you need two surgeries. The first surgery, you harvest cartilage from non-weight bearing areas, and then you close the patient up, you start take the cells, culture the cells in vitro. Once you get enough cells, then you go for the second surgery, maybe a couple of weeks down the line, and you clean the damaged area now, and you place a collagen membrane on the defect and inject the cultured cells. The cells will now be present there and they will help in regeneration. Chondrocytes can actually secrete the matrix they need to culture, they need to grow on. So, the idea is have these chondrocytes there, and hopefully they will secrete the matrix and they will heal the tissue. So, there have been 3 generations of this. The first generation is where, which I just explained. So, all you do is take a chondrocyte suspension, which is and you inject it under a periosteel flap. So, this is a small flap which is sutured on top of the damage, and you take out chondrocytes which have actually been cultured, and this is now injected inside it. This is just the flap is just to make sure the cells do not leak out of the place. It will hold the cells there, and hopefully this will help in regeneration. And this was the next generation, where a chondrocyte suspension is injected under a collagen membrane instead of using a flap which is again harvested from your own body. So, here a collagen membrane was used, and this has actually been reasonably effective. So, recently what people have been doing is they actually culture the chondrocytes on the scaffold, on a collagen scaffold, and then place it in the damaged tissue. So, this has also been quite effective. So, this is now identified as the 3rd generation of autologous chondrocyte implants. Okay. So, this basically gives a summary of what are all the different cell based techniques and biomaterial based techniques which are being used. So, we will discuss a little bit about molecule based techniques, signaling based techniques which are currently available. So, signaling molecules are usually not used by themselves. So, because these are growth factors or proteins which need to be delivered to the site. So, they are usually loaded to some material and delivered. So, we will look at what are commercially available and what is currently being done in that domain, and with that we will come to the conclusion of the basic introduction for tissue engineering. Okay. Thank you.